Good morning, good afternoon, good evening. Welcome back to chapter 15. We're talking about what happens after a mass extinction. What happens after a whole bunch of species have been wiped out. What happens is this process called adaptive radiation. And we kind of threw this idea out in chapter 14. Let's explore it a little bit more now today. Remember, in an ecosystem, there are a lot of jobs to be done. There's making the food, there's eating the food, there's cleaning up the mess of the food. There's a lot of different jobs to be done in an ecosystem. With a mass extinction, what happens is a whole bunch of individuals die. A whole bunch of things are wiped out. Well, now there's a lot of jobs that aren't being done. So I've got a population of organisms that survived. That population, now because individuals naturally want to spread out, when they find a new area that's not being colonized, they will move into it. They will exploit resources that aren't being used. Oh, well, nobody here is eating this food. Well, we'll just go sit over here and eat this food. This is adaptive radiation. They radiate out from a central population of survivors and give it several generations. We're not talking about a couple of years. We're talking about a few decades or a few centuries. A century sounds like a long time to us, but what is 100? If you have $1 million and you loan $100 to somebody, what does that mean to you? Is $100 any kind of money if you have $1 million? No, $100 isn't that much. Keep it, have it, whatever, I don't care. So now, what is 100 years compared to 1,000,000 years? Not much. What is 1,000,000 compared to 1,000,000,000? If you have $1,000, how much is $1? Not much. There are 1,000 million years in a billion. After a mass extinction, you have some individuals that survive. You have some populations that will live. And if you give them enough time, a few centuries, they will move out and radiate out into these areas that aren't being occupied. Plants will begin to sprout in places where there's dirt but nothing else growing. After the plants show up, animals show up, so on, so on, so on. So following a mass extinction, there will always be colonization of these new unexploited areas. Plants show up first. After the plants show up, the animals show up. So mass extinction. After every mass extinction, there's also a massive speciation event, an explosion in new species. I know you can't see this. All I can do is encourage you to make sure that you've downloaded the PowerPoint and look at this graphic, blow it up on your tablet so you can see it. The reason why I want you to look at this is right here, this is the end of that Precambrian era, that first 4 billion years. Remember when the graphic went all the way across the TV and the last 3 eras were only like that big, right? All the way over here. Well, that breaking point right here is right here. So this are those last 3 areas. Notice how it's broken into sections of its own. And we're not going to talk really about the sections of its own, but I just wanted you to see that each of these 3 other eras in the history of the planet, they're broken up into their own sections. And again, these dividing lines. What are these dividing lines? What happened at these dividing lines? Global catastrophes, mass extinctions. This right here is the breaking point between the Precambrian and what we call the Paleozoic. And the reason why it's called the Precambrian is because this first little column right here, this first little row right here, is referred to as the Cambrian. And so what came before the Cambrian was the Precambrian. The Cambrian begins with this thing called the Cambrian Explosion, an explosion of new species that we did not see before. The species that we saw before this time are all gone, an explosion of brand new species. This very first section, second now in the history of the planet, Precambrian, and then that leads to the Paleozoic. This right here is that 600 million years ago mark. This is the Paleozoic. It has several different sections of its own. A couple of them that are interesting is the Cambrian that we talked about. The next one is this one right here called the Carboniferous Period. Carboniferous. What does fair mean? We talked about this. Fair means to bear or to possess. It is the what-bearing period? The carbon-bearing period. Carboniferous. The reason why it's called the Carboniferous period, and this section right here is about 60 million years. The reason why the Carboniferous period is important is because at this time, plants developed this new compound called lignin. Lignin means to glue. What's important is that nothing was able to break down lignin. Remember, decomposers, mushrooms rot wood, mushrooms rot plant matter. They recycle those nutrients back into the atmosphere. Plants develop this new compound called lignin that fungi cannot break down. If they can't break it down, what does it mean then when a log falls over and dies? It means it doesn't rot. It means it lays there. Until when? Until another tree falls over on it. Imagine, I want you to do the experiment yourself. Go get a bowl and go get a handful of toothpicks and throw those toothpicks in a bowl. That's what forest floors looked like during the Carboniferous period. But instead of toothpicks, you're talking about gigantic trees. As the dirt built up, it compressed these corpses of trees, and over hundreds of millions of years, the corpses of those trees were squished and squished and squished and turned into the stuff that we call coal. When you break apart some versions of coal, guess what you find inside? You find imprints of leaves. You find imprints of tree bark. The Carboniferous period. All of the energy that we're currently burning right now, coal, oil, and natural gas, all of the carbon that was taken out of the atmosphere and locked away underground through this process called photosynthesis, was taken out of the atmosphere right here in this period. This period is about 300 million years ago. That's how long ago all that was taken out. The Carboniferous period. When we say that coal, oil, and natural gas are fossil fuels, we're not burning dinosaurs. Dinosaurs! We're not burning dinosaur bones. The fossils that we're burning are fossilized plants, and they're not even fossilized plants. It is coal that's been made out of plant parts. After the Carboniferous period, we begin this stage called the Permian. And the reason why the Permian is important is because it leads us to our last period within the Paleozoic. And it is ended by this thing called the Permian extinction, which is another major extinction event. To understand why some mass extinctions occur, we need to understand this process called plate tectonics. Plate tectonics. The ground that you're standing on, the ground that the foundation of your house is built upon, is on a floating slab of rock called the North American continental plate. Those plates are floating on lava underneath of them. When a volcano erupts, it's that the lava underneath is shooting out. Very much like when you were in a pool and you put your hands on the surface of the water, you squeeze your hands together and it squirts out a jet of water, right? That's what a volcano is. Except instead of hands, it's the top of a mountain. The pressure from underneath shoots the lava out. Because a giant slab of rock called a continent pushes down really hard on this stuff called lava. These plates move around. They don't stay still. They move about as fast as your fingernails grow. The North American plate is currently moving away from the European plate at about the rate of 2 inches a year. So 2 inches a year. America is getting farther away from Europe. And it's getting closer to Japan by 2 inches a year. And you go, 2 inches, what does it even matter? Who even cares? Well, what's 2 inches times 100 years? Oh, well, that's 200 inches. That's like 8 feet. So since 1900, Earth, the North America has gotten about 10 feet further away from Europe. Okay, we'll compound that times 1,000 years. Well, now we're talking like a quarter mile. Okay, compound that times 10,000 years, times 100,000 years, times 1,000,000 years, times 10 million years, times 100 million years. And when you multiply it in those, what we call geologic time, when you multiply that movement by factors of millions, now these plates move around. And a way I want you to imagine it in your head is I want you to imagine a swimming pool. And on that swimming pool, we take a bunch of floats, and we throw those floats, 4, 5, 6, 8, 10, we throw those floats on the pool. And we're going to put a camera up that's going to do a time-lapse photo of that pool. Are those floats going to stay still right there, right where you throw them? Or are they going to gently move around and drift around on the surface of the pool? They're going to drift around and move around on the surface of the pool. Might there come a time where several floats come together and then drift back apart again? Might there come a time when a few floats come together and then separate back out again? And you're going to watch this over the course of a whole day or a whole week. And you're going to watch the movement of these floats. And that's what the continents do. But instead of an afternoon, what happens is this takes place over the course of hundreds of millions of years.